Welcome to this course on TCP-IP. Let me first introduce the team of people who will help you with this course. So I am your teacher. My name is Jean-Yves Le Boudec. And here is the team of teaching assistants. Stéphane Plassard, who's sitting here, is the head TA. And we have a fine team of PhD students and postdocs. Pluton Grammatikos should be in the room somewhere. Here. Chonak Kar, Hossein Tabatabai, and Ludovic Thomas. Good, we get the picture back. We also have 4 student assistants who will help us primarily for addressing day-by-day questions. Who are not in the class today, I guess, and who are master students who took the course last year. So this course is primarily for communication systems and computer sciences. It's also taken by a number of you who are in other branches of engineering, because many systems today, in particular in cyber-physical systems, are interconnected. We can start from scratch. Of course, we hope that you are used with programming and comfortable with the computer. And we will practice with computers in a virtual environment. That's for a few years. In the past, we did the labs on physical machines and routers. And now it's much more convenient using a number of virtualization technologies to do it on your own computer. So there is a significant amount of time that you're expected to spend on the labs here. Before diving into the course, let me also mention that in the computer networking community, there is a long-standing tradition of zero tolerance for any kind of discrimination based on origin, gender, sexual orientation, or any other reason. So we will adhere, of course, to this philosophy, like everyone at EPFL, I hope, does. And if you have problems of any kind of any harassment, you know that there are places where you should go and complain. And now, since you're putting a foot into that computer networking community, I trust that you will all follow those very strong traditions. One of the problems when teaching a course like this one is that every single chapter of the course is very easy. It's not like information theory or linear algebra. There's no real difficult part. That's the good news. But the bad news is that there are thousands of them. So the problem is, how do we teach and how do we learn something that has a large description complexity that comes from the accumulation of a number of little things? And you can teach and you can learn something by knowing nothing of computer networking and going on the forums on the web and find a way to install or program a socket or whatever. And perhaps it will work, but perhaps also you'll do wrong things by doing that because there might be background information that is missing. But that is the problem of how do we cover the breadth, given that we also need some depth in all of the topics that we study, otherwise we're just not operational. One of the techniques that is used by several teachers for such a course and similar systems-oriented courses is to use what we call the rake philosophy. In French, la philosophie du râteau. This is a rake that goes deep into a number of selected topics that cover the breadth, but we will not go deep in every single detail. So there will be lots of specific topics where we will not go into all the details because, one, we don't have time. Second, it would be boring. But so that if your expectation is to know everything on how a specific type of modem works, or how do I do this or that operation in BGP on the Juniper router, we will not do that because we will not work with Juniper router. We will work with BGP, but not on Juniper routers. But the hope is that because the practicals and the topics that we study in the course cover all the depth, all the breadth, and we go in depth into a small number of topics. In fact, in the 7 labs of the course, we'll be forced to go in depth into some of the topics in theory and in practice. And the hope is that by that, you're able to interpolate. If anything goes that you have not seen, then you should be able to have an easy understanding by simply interpolating from what you know. And the second technique to help with that complexity, and I think this technique applies to everything we do in computer science and perhaps even more in engineering, is to make the difference between, it looks stupid, but very often it's forgotten, make the difference between why and what on one hand versus how. If I go on the web to see, I want to send a packet to an application that's doing that, and I will easily find a checklist that will say, install this, install that, click there, say yes to this, change this file by opening this folder, and etc. You have a checklist. That's the how. So the internet is very good at telling us the how. But very often, the how has a large number of details that are system specific. I mean, where in this version in Linux is the configuration file that controls which version of TCP is used? Okay, that's something you can easily find. Is that something you should know by heart? Probably not, except if you change configuration files for TCP, that's your job, and you do it every day, but very few people do that. In contrast, if you think about the why and the what, usually that's way simpler. Why is this thing invented? Why do we do packet switching? Why is an IP address the way it is? Those are questions that you should ask yourself before diving into the how. Because if you do this, first, the why and the why are short. So those are the things that are worth learning. And this is what we will focus a lot in this course. Also, because most of the time, when we have understood the why and the what, we're able to guess a lot of the how. If we're familiar with the system, for example, after the lab, you will be familiar with the type of routers that we use in the lab, and the commands that we use there, they will sound familiar to you. So if you have to do something that we have not done in the lab, you will easily find it. Wikipedia is usually, and the internet in general, is usually good at the how, often less good at the what and why, though it should be. So I encourage you to, whenever you read a Wikipedia page that you find is not explaining well the why and the what before, please edit it to improve it here. So that's really very important. And very often, even when we hear a technical presentation, we hear a long story on how I do this and how I do that, but I don't even understand why are you doing this and why not. So this course is, of course, focusing on the why and the how. That's the theory part, if you want. But of course, we cannot separate the why from the how to do it in practice. Otherwise, you would be a lame duck, you would have only one leg. So we need to have those two legs of understanding the theory and having some hands-on experience with the practice. When I say theory, again, don't expect much theory like there is in a signal processing course, but there is a theory. So, which we will discover by addressing a number of why and whats. The computer networks, the way they are built today, is the result of two things. Is the result of people like us here inventing this. So people that were my generation 35 years ago, they had to address solutions like, how do I prevent congestion in a router? Nobody has this problem today because this has been solved already. Now, our problem today is to learn how this is implemented and how it works and what are the side effects. So it was invented by engineers. So it's not arbitrary creation of physics, where in physics we discover the law. I mean, why is the electron this way, is behaving in a quantum way in that form? We don't know, but somebody did experiments and saw that the electrons have some properties, but it was not invented by us. We just observed. Here it's invented by us. We human beings are entirely responsible for the internet the way it is. So because it's invented by us, and most of us are similar, once you understand the why, you guess, and you probably do the same in many cases as the original inventor. And if you don't do the same as the original inventor, that's the interesting thing to remember. This is where there is information. This is where there is entropy, where your answer, your guess is not right, then you have to learn that and remember. If your guess is right, you can forget. You don't need to continue to learn the details. So that's the first thing. It has been invented by human beings. And then there's the evolution. The thing has evolved from a given historical path that I will also give some few hints about how it is. And this is why things are the way they are today. In particular, we will discover that there is the MAC layer, IPv4, IPv6. Nobody would do that today if we would say, you have to create the internet. We're after World War III, the world has collapsed, you have to redo it, but we've kept the books in printed form so we can learn what has been done. You have to reinvent the internet. Probably we would do an internet that would have no MAC layer and only IPv6. We would do that immediately. But this is not how it is today, as we will discover, perhaps painfully, perhaps with pleasure. So we will do labs, 7 labs in total. You will discover them in one by one on Moodle. We use Moodle exclusively for all information. And we use quizzes for the labs, for returning your parts of the lab, which help you. Every lab is modular, is meant to last for 2 weeks, and every lab is broken into 3 to 4 pieces, and you have to do them completely before continuing to the next one, but you will receive immediate feedback through Moodle quizzes. Also, we do post on Moodle lecture quizzes. So there are small quizzes, sometimes very easy, sometimes some question might be a bit more tricky, that you have to do every week. There's one every week. So there's food for you every week. And they are daisy chained. You have to do quiz 1 before being able to do quiz 2. And you have to do quiz 2 before being able to return your answers to the first lab. So you have to do it every week. It's very easy. If you follow the lecture and everything is fine, the quiz is done between 10 minutes to 30 minutes. So it's no big deal, but it's also an opportunity for you to tumble and use this thing that I said before. If you discover that things are not as you expected, that means there is something that your brain is not well aligned with the theory, so you should learn something there. It's very important to do it, also because, as I mentioned, there's a lot of small things, and the only way to learn a lot of small things is to do it incrementally. Of course, there will be an exam, so there's no midterm, there's only a final exam, which is closed book. So you will not be allowed to have a book. In the past, I did it open book, and then I had a problem with a student who took the oral exam, and he knew nothing of TCP/IP, I failed him. But then he complained that he was not in the condition of the written exam because he could not read the book when I asked him a question, and so I had to give him the credit. So I made the exam closed book, and to my surprise, the failure rate went practically to 0 after becoming closed book. So it looks like open book is not a good idea for a topic like this one. Of course, I don't ask that you know by heart what are the bit number 23 in the IP header and things like this. So we publish an exam booklet, which is already available on Moodle of the course, so you can know what you don't need to know by heart. All the rest that is not in the exam booklet, you should know. Right? You can look at the exams of the past year to see also a feeling what you should know. And we will not use a computer, which is a bit paradoxical for a computer networking course, but we have not found a good way to make an exam that is guaranteed to be free of cheating with the computer. Reflecting the fact that the theory, there are 2 legs in this course, theory and practice. The final grade is also the average of the theory and the practice. The theory is the exam, and the practice is the labs. In every lab, we acknowledge the fact that not all of you perhaps have the same time to devote to this course. It's 8 credits, so it's a big course. You should devote enough time to corresponding to the volume of credits. But depending on other priorities at other points in time, some of the labs are bonuses. We call them research exercise in the sense they're a bit more, they require a bit more initiative and independence. There's nothing to lose if you don't do them, but other than time. But if you're motivated, you can do it, and they will give you a small bonus to the lab grade. Voilà, that's all for the organization part. Are there any questions? Yes? So the question is, we bring the laptop in class? For the lectures, no, but you should have a screen, a smartphone or something, because I will do speak-up quizzes, but you don't need a laptop. Although when I take a class, I'm always happy to have a laptop because sometimes there's a term I don't understand. I look it up on the internet, but that's your personal choice. For the labs, you need your own laptop. Right? And as is posted on Moodle, we use a virtual machine that works only on Intel processors. If you have a Mac like this one, oh no, this was an Intel processor. If you have a recent Mac that has an Apple processor, it won't work on it. So you will not be able to do the labs on our virtualization system. We hope one day this gets solved, but we're not able to solve it for this course. So we will have for you other computers, small computers, Minix, that we will lend for you for the duration of the semester that has an Intel processor, if you're in that case, so that you can all have your own computer. Yes? Question? AMD? No, that's the problem. Yeah. There might be, it depends if it's same processor instruction set as the Intel processor or... What computer is it? Yeah, then it will work. It's compatible with the internet. It's only the Mac, the very recent Mac. If you bought a Mac more than 2 years ago, you don't have the problem. If you bought it recently, and it's depending on the type of Mac, you may have the problem. Okay, other questions? No, then without further ado, we go to the next chapter. The next chapter is not very typical of the courses, of the rest of the course. We will go relatively superficially here into a complete view of the computer networking architecture. So we will, if you want, in 1 hour, a bit more than 1 hour, cover everything. Of course, we will not cover everything at depth. It will be the purpose of the course. But for the labs and for other things, we need to have a global view first before being able to do anything. We cannot study the Mac layer during 2 weeks and not being able to do anything with the entire system. So we will do the course in 2 rounds, if you want. The first round that will last today, and the rest that will last for the rest of the course. So this is a high-level introduction. For some of you, some of it might be familiar, then take it as a rehearsal. So when we talk of computer networking, the first word you will see is layers. So that's a word that is used practically only in this context. So what is layer? A layer is simply what we call in other areas of engineering module. When you build software, hopefully it's modular. And being modular, there is an interface, a well-defined interface on how you use the module. What is special about the layer is that the interface is not just to other modules in your system that talk to it, but also to other similar modules of other systems. For example, if I send, the application layer is in charge of things like the web. When I have the code that embeds my web browser, it has to speak to the lower layers, to the rest of the machine, to be able to send data and receive data. So it has an interface to the lower layer, but it also has an interface to another machine that's also speaking the same language as used for the web, for example, a web server. So the fact that there are 2 interfaces, one horizontal, one vertical, is what makes this modular approach deserve a special name called layer. That's all. Very often in books or courses, you hear that there are 7 layers. Now, there are as many layers as authors would like to have it. But most authors agree that in the TCP-IP world, which is the world where we are, most of computer networks operate only with TCP-IP, we have 5 layers. And as I mentioned, one of them might be a bit redundant, but this is how it is. So the 5 layers corresponds to dividing the functions that the network should do into communication. That's the useful part. That's what we really want to do. The interconnection, that has to do with physically or interconnecting the systems together. And the physical layer has to do with solving the distance problem. So the application layer, we all know it. For example, this is what happens if I go to a website. My software somehow will get some information about an localization of a resource, which is, for example, the name of a file here. We will come back to this thing. So this is the name of a machine, and this is the name of a file in the file system that is routed to the web server that is here. So that's what the application would do. And then this, of course, gets translated into application layer messages. For example, if we sniff the packets, which you will do in the first lab, if we look inside the packet, we will see there are things like these words, get, and more, which are part of the HTTP protocol. So HTTP is the language that is used by the web here. So you will do your own application layer when you will program sockets. And this is also where end-to-end security is residing. So that's the easy part. In fact, the only thing we're interested in computer networking is the application layer. But it's the only thing that we will not describe in much detail in this course. We will look at all the things below, because the application layer itself is the topic of other courses, in particular, information systems and distributed systems. For some reason, the application layer uses not directly the network, although there are some systems who do this. There are small-scale industrial networks where you write a program that uses a primitive that results into a packet of data being sent directly into the Ethernet adapter, for example. This is old stuff that exists in industrial networks. It does not exist anymore today in large-scale systems. Instead, when an application layer program wants to send or receive information, it uses primitives called sockets. That is, in Lab 3, we will use that a lot, and I'm sure many of you have already played with that. And the sockets are the service that is provided by an intermediate layer called the transport layer. The transport layer in TCP formally exists in two variants, UDP and TCP. The goal of the transport layer is to provide a programming interface, is to provide the sockets. So, which is a programming interface for anybody who writes a program that communicates. And when you provide such an interface, you need to do, of course, an interfacing. So any interface comes with some overhead, but you need to do two specific things. One is easy to understand for TCP, is called reliability. We will discuss a bit later. We will in large details. The internet uses packets, so if I send you a video file, you will not be sent as one unit, but it will be broken into smaller pieces called packets. Talk about that a bit more. And some of the packets may be lost. Why they get lost, we'll talk again about that. And knowing that some of the packets may be lost is something that the application must do. So if you write an application layer, you have the choice. Either you use TCP or UDP. If you use TCP, that means the consequences of losing packets are taken care of by TCP, not by you as an application program writer. So of course, most of the time we want to use TCP. So TCP is the normal thing we use, because if a packet is lost, then it will be, in fact, the loss will be repaired by primitive ways, by repeating the data by TCP. TCP do therefore reliability. It does different things also for reasons that are purely historical. TCP provides what is called in-order delivery. So if I have a video file to send to you, my TCP will break it into perhaps 1,000 packets. And then this system, TCP, will make sure that the packets are received by the other end in exactly the order that they were sent. This is what TCP will do. It's called in-order delivery, and it's called a stream service. So why is it done? Well, because when TCP was invented, the mental model was to replace physical wires. I mentioned that it was possible, and that's very old in history, it was possible to write an application program that would be directly connected to a physical cable and would send the packets directly in the physical cable from A to B. It was possible, and I did that many, many years ago with a token ring and things like this. When TCP was invented, one of its mental model was to replace this, emulate this. When A sends to B, it is as if A would be directly connected by what is now called a virtual channel, or more frequently a TCP connection. And people believed when it was done, it's a good idea to do that. As we will see now, nobody believes it's a good idea anymore, but that's the way it is, and we'll have to live with that. And it has sometimes negative side effects. But it means, in particular, if you're an application writer, you send information via TCP, you don't need to reorder the blocks of information when they are received. For example, if you're transferring a file over TCP, you can write the received blocks into a file incrementally as they are received. You don't need to have an offset and things like this, which you need to have if you use UDP. UDP doesn't do that. UDP is simply giving the most direct access to the network as possible, which means that if I write 1,000 packets into UDP, UDP will send the 1,000 packets. Some of them might be lost. It is your responsibility as application program developer to detect the losses, or perhaps you don't care. Perhaps sometimes you don't care. For example, if you're in an airport, you're refreshing the screens with arrival information, and you send a refresh every second. If it's lost, the next second will be repeated. Perhaps you don't care. But most of the time you do care, so you should do something about it. And the order in which the packets are received might not be the order in which they are sent. So you must put numbers, packets, and things like this. Question? The question is whether in UDP the content of the packet is guaranteed to not change. Yes, with high probability. So in principle, there is a checksum that we will see is UDP, in UDP is not always used, but is present, so the application can use it. And there are also other mechanisms in Ethernet, Wi-Fi, etc., to make sure that the content is not changed. So, of course, once in a while, that happens with probability 10 to the minus 20. So once in a while, the content might still be changed. So over the exabytes of information that are exchanged over the internet, there are errors, there are residual errors, but they are rare. So that's the first thing to remember. Now, UDP versus TCP, the major difference is UDP is not reliable. UDP is essentially doing nothing, as we will see. It does one little thing, but essentially it gives you a raw access to the network. TCP gives you a sophisticated interface where if anything goes wrong, it will take care of it. We'll see it does zillions of other things like prevent congestion. And so that relieves you from doing this. With other side effects, in particular in UDP, the unit of information is the block that you write into UDP. If you write into UDP socket 3 packets, then they will be sent to the, and if they're not lost, the destination will receive 3 packets, broken in exactly the way you broke them, which seems obvious, right? The post office doesn't re-break your packets into pieces and send you pieces of it. But TCP does that. TCP, as a streaming service, the unit of information is a byte, which means that if I write into a TCP socket 10,000 bytes, I send them, if I write 10 times, let's say 1,000 bytes, by doing 10 calls to the TCP socket, I have no guarantee that there will be 10 packets of 1,000 bytes. There might be packets of 500 bytes, because for whatever reason, TCP believes it's better to have 500 bytes packet, or packets of 300 bytes. That means that the second call might be coming at the end of a packet, where the data that's at the beginning of this packet is the end of the first call I did. So of course, it will preserve order, but it will not preserve the boundaries, which means the application has to make boundaries with TCP. So TCP is not entirely free. TCP does not give you the boundary between messages. In fact, the mental model of TCP, when we write into a TCP socket, it is like writing a file. We write into a file by putting all the bytes one by one into a file. When we finish writing, we send an end of file, and then that's it. So it's exactly the mental model of TCP. Those are the basic things that TCP/IP provides, nothing else. Why is it like this? Well, that's due to history. UDP is the simplest, and TCP wanted to simulate something very powerful. Of course, people have realized this is not sufficient. So all possible variations around this, for example, a reliable message-oriented protocol exists. So there are things like STCP that would provide messages in a reliable way, etc. But none of them are not very much used. The only thing that starts to be used a lot is called QUIC, which we will review a bit later, which is a kind of super TCP. It solves many of the problems that are caused by this design of TCP and uses UDP. which might seem weird. I mean, since it's transport layer, we should have a third transport type, which is quick. But again, that's now the weight of history. Now networks, routers, NAT, modems, gateways, everything exists. And now one of the key reasons that triggers evolution is what, according to you? What are the things that cause evolution to happen at a fast pace? In biological as well as physical systems, yes? Disruptions, yes. Money, sure. But there's one more important. Malware. The biological systems, they evolve by viruses that carry DNA all around. And the internet is exposed to constant attacks. So the internet, if you open a server that is unprotected, in the seconds that come, you will have hundreds of packets that are trying to find open ports and do attacks on your server. So we have to realize this. Just like we're not living here in a sterile environment, we have an immune system that helps us get along with all the bacteria, viruses, and so on that are floating in the air. Not all, sometimes, but most we do well. The internet is the same. The internet is full of attacks, full of bad things that happen everywhere. And because of that, that limits the possibilities of evolution. For example, most routers and computers, they have a lot of things called firewalls and so on. They inspect packets that come, and whenever they find something unusual in a packet, they're not happy, they kill it. This is why now when the routers, they look whether a packet is UDP or TCP. A packet that is neither UDP or TCP is suspicious. So most of the time it's killed. That's why if you invent a new transport protocol, you have to make it in UDP or in TCP. This is what QUIC did exactly. I said that UDP does nothing. In fact, it does one thing, which is carry what is called a port number. So that our first addressing information we find. What is a port number? Well, we see it everywhere. For example, the standard port number for the internet is 80. For DNS is 53. And there are also other port numbers that the numbers don't mean anything. Why do we have that? Because typically from machine A to machine B, there's not only one communication. If I go to a web server, my machine will go to a web server somewhere, and the web server will reply to me, but my machine is not used exclusively for this interaction. I don't have just one TCP connection on my machine, but typically have many. Why do I have many? Well, one that is very easy to understand is I will need to go to the DNS to find information before going to the web server. So we'll need to have auxiliary things. Plus, when I open a web page, I might click on several things, or might even have several web browsers on a window open on my machine. And I have lots of application programs. Perhaps I have Dropbox that's running in the background that uses its own TCP connections to do a number of things. So typically, we have a number of tasks or processes that are communicating on one machine and also on a web server. Hopefully, the web server is serving hundreds of thousands of customers and not just one. So the port number is used to multiplex this thing. So here, if I am process PA that's communicating with someone else, then this process PA will need to get what is called a port number on from UDP, for example, 1267. This port number means nothing. It's just you need a number, like the number of the box where the data that is for you will be put into. And if this program is killed and restarts, perhaps it will get a new one. In contrast, the well-known port numbers are reserved for services that we want to access by default. For example, DNS is typically 53, which means that if my machine goes to a DNS server and wants to talk to the DNS server, then it knows it is port 53 by default. That avoids the chicken and egg problem. Is for me to communicate with you, we need to agree on the port numbers that we use. But how can we agree if we have not yet communicated? So we need an out-of-band mechanism to set some defaults. One out-of-band mechanism is to have default values, 53, 80. Another one is I communicate with you because I've received some information that indicates that I should go to you. And this information might contain the URL and the port number. Sometimes you find that when we go to a machine like here, at the end, we might have here, the port number might be indicated here, or it might come from outside. So when when some data flows from A to B, of course, there will be indication of the source port number, 1267, and destination port number 53, which has the result that the operating system, when it receives information, will know this is for this process. And when this process will reply, then it will reply to the source port number, and we will know it is my web browser or whatever my client, DNS client resolver that needs this piece of information. Of course, we need to associate a process with a port number. This is the binding, and we'll talk about this when we see the socket. This must be done. It doesn't come automatically. So that's the transport layer. We'll come back to it in a number of details, but that's the very first thing we need to know, and particularly port numbers. Now, the basic problem of networks is, of course, to interconnect everyone. So we want to interconnect all the computers in the world. And the simplest way would be to draw wires between all computers, which was originally done, not physically with wires like this, but physical connections that were using the telephone system. So the very first computer networks were using modems that were really calling the phone number of another computer. So if you have two telephones and you create a telephone connection, now it's all IP packets, but 30 years ago, it was, or let's say 100 years ago, it was truly a physical copper connection from A to B with ladies in the switching offices that would exchange jacks to make the circuit. Now, of course, it's all IP packets, but that was the idea of at the origin. So this is exactly what the network layer is providing. It's providing the ability to connect any device, computer, smartphone, anything, to any smartphone here. But of course, direct connections are not possible because there's a scalability problem. So what is done is, what was done historically, is to have intermediate systems that are used to solve this full interconnection problem. So the classical problem, if you have a big organization, you want everyone to be able to communicate with everyone, then you go via management. So you talk to your first line manager, who speaks at the next meeting to the second line managers, who talks at the executive and sends the information back. That's old style management. And it's not very pleasant, but that's how the very first computer networks were done. So also you have to remember, we're talking here of the 70s. In the 70s, the computer was a big thing. There was one big computer on a campus. Then there were so-called mini computers of the digital company. There were perhaps 4 or 5 mini computers on a campus. So there were very small numbers of computers. Most companies did not have computers. Only large companies had computers to do the payroll and things like this. So they were called mainframes, so big computers, and you were connected to the computer with simply a screen. It's shown here as a PC, but in fact, it was just a teletype, a screen and a keyboard. And whenever you would type something, it was echoed back to the screen here. And this computer was therefore time sharing between all those screens here. And then, so this is a single mainframe isolated. When you wanted to interconnect them, then the simplest was to use some computers as mailboxes. So if you had to exchange a message from one to the other, the message was entirely transferred from this computer to the memory of that one, and until it is read or delivered by the destination. That was the first computer networks. They were called SNA, for example, the IBM SNA, the Multics computer, were using that principle. But very quickly, in fact, in parallel, so those were the first commercial networks. So for 10 years, commercial computer networks were like this. And if you would be doing business with computer networks, that was it. But in parallel, there were research networks, the CCLAD network in France, and the DARPANET network in the US, which have invented the idea of packet switching. So instead of having the file being transferred, we break the file into smaller entities, which were at that time a bit less, a few hundred of bytes, which are today classically 1,500 bytes. And the main idea is that each of those blocks of data is like a postcard. It's a standalone entity that can be sent via the network. It contains the destination address in particular, like a postcard does. If I send you a postcard, I put your name, your street address, and if I want to send you a long message, I might send 5 postcards, and then you will receive them. And this is exactly how it works here. So the result is now, if we send messages, for example, the message here fits in 3 packets, then we still have mail servers, because we don't send a mail typically from my computer to your computer. We send mail from my computer to my mail server, who sends it to your mail server, might be the same if it's EPFL, and then you log to the mail server to get it here. But between mail servers and between computers, the data is sent into packets. And here, we also see a number of strange things. We've seen that some of the packets were not all going the same paths. That's very typical of the very old style internet. Still exists in the internet today. We try to have all packets of the same flow use the same path, but there are many, many redundant paths in the internet, so it's never impossible that packets follow different paths. In fact, it's part of the design of the internet to have a lot of redundancy, so that if something crashes, we will compute another path around it. We will see how to do that in Lab 4. So that's the major innovation that was done. Now, why do you think it was done? That's the opportunity to do our first Speak Up quiz. So we will speak up in this course. For that, you have 2 options. You can simply go to the website of Speak Up and say yes to what they require, and which is web.speakup.info. There's also a Speak Up app if you prefer, as we will use it a lot. And then there's a room number, which is given here, that will, at least for this week, it will change every week, or we'll write it on the board every week. So here I'm proposing 3 possible reasons for why people like in the CCLAD network and in DARPANET, why they thought it's a better idea to break the data into smaller chunks. Is it because it reduces the buffer required in routers, or because it improves the performance in terms of bit error rate, or because it increases the capacity of the links in the sense of information theory? So what is your best guess? I close the poll in a few seconds. And the majority, you should see the results of the poll on your display. The majority says A, which is the correct answer. In fact, at those times, the intermediate systems, so the specialized computers that were transporting the packets from one input to the output, the most expensive part of those systems at that time was memory. Remember, we're in the 70s, so we're talking of kilobytes of memories and perhaps hundreds of kilobytes. This is illustrating what happens on what is called time and space diagram. That's something we'll use several times in this course. That's a useful way to reason about distributed systems, where I'm showing space on one dimension and time on the other dimension here. And here I have a computer that sends a packet to store and forward, so using IBM SNA, for example, to another computer that receives it and resends it. We see 2 things. We see this dimension, which is the time it takes to send the packet. This is given by the bits per second of the link. If you're 10 megabit per second and you're sending 10 megabit, it would take 1 second. So the time it takes here is the time given by the technology, the megabits per second of the line on which we're sending. But we see here that the thing does not arrive instantly. There is a difference here, difference from here to here. What is this? Yes? The time it takes to arrive, not exactly, the time it takes to arrive is here. Here I've received the last bit. Here it's not even the first packet, it's true, It's time it takes to arrive, but that's due to propagation of light. So all computer networks, quasi all, use light or a variation of light, electromagnetic waves that all propagate at the speed of light, which is very fast for us in this room, but takes 200 milliseconds to go around the Earth. So when you do a ping to New Zealand and back, that's 200 milliseconds, which for the speed of computers is not negligible. Might be negligible if I'm connecting this to that, but is not if I go a long distance. So that's the speed of light this time here. That's the beginning of the first bit, does not arrive instantly. But what we see here is that the intermediate system here has to store all this packets to all this message before forwarding it. Whereas if I break into packets, then after receiving the first packet entirely, I can send it, which means I need to store, in this idealized case, only one packet at a time, instead of storing the entire file. So if I send a file of 1 megabyte, I never need to store 1 megabyte in this intermediate system. So this is the ability to do what is called cut-through, which primarily was motivated by the requirement to reduce the required buffer. Also has another positive side effect. Delay is reduced, because as you can see here, the time I've finished here at the end is less than here, because I don't have to receive entirely at the intermediate point. Capacity or bit error rate were not motivated. In fact, they're not affected by that. They're not the reasons for packet switching. So packet switching is the solution today. I mentioned that all systems, quasi all systems, use light or electromagnetic waves. So Wi-Fi in this room is using electromagnetic waves. Cable Ethernet uses Ethernet or similar technologies over copper most of the time. There are a few exceptions. For example, there are acoustic networks that use acoustic waves, and then the speed of is, of course, much, much slower. So this is used, for example, in submarine networks where sounds do propagate under the water, but not light. So networks use packet switching, and they have addresses. So the other important thing in a packet when we use packet switching is that we put the final destination, the address, which is like the zip code of your street address. Here is the kind of addresses we have at EPFL if we use IPv4. So those are all, I'm showing here a simplified version of a snapshot at one point in time of EPFL. I'm showing also a part of our sister school, ETHZ. And between us, there is a switch network. Switch is the equivalent of Swisscom, if we want. It gives us long-distance connectivity. Do you notice anything special? Well, there's plenty of things we see here. We see all addresses have the same format, right? There's something, dot something. So it's a block. There are 4 blocks with dots. Every block corresponds to 1 byte. It's the coding of 1 bit, 1 byte, 8 bits of information, coded in decimal. It's coded in decimal because it was done in the 70s. If we would invent it today, we would code it in hexadecimal. It's much more convenient to encode bits into hexadecimals because 4 bits correspond exactly to 1 hexadecimal digit, whereas here we have 8 bits that correspond to a group, a number, which is between 0 and 255. Anything else that you notice? Yes?
With every subnet, you change the IP.
With every subnet, you change the...
For example, INF billing is under 71.
Yes.
At 1.8 months, 71, that's something with when you go to
Exactly. So the theme here is that those addresses, they are not random numbers. They have some structure that means something. In fact, here the structure is that anything that starts with 128.178 is EPFL, and also 128.179, which corresponds to how many bits? This is a prefix of 16 bits, but since there is also 179, that means it's in fact 15 bits. So EPFL has a prefix of 15 bits. So there is a block corresponding to the prefix of 15 bits that says to the world, this is EPFL. Only EPFL owns these addresses. If it's legally assigned by someone, it is by EPFL. And we see ETH has another block, and the switch has other blocks here. So there is some structure. We'll talk about this. Of course, this structure is it's not as simple as that. An EPFL number, when you're using the VPN, you might be roaming in China, and you're using the EPFL VPN, then you will have an EPFL address. We will talk about that, but that's the first thing to remember. It's 32 bits, 4 blocks of 8 bits, and there is a structure in the IPv4 addresses. Question?
Address like 15.221.
It's just because I was lacking space, so it's 128.178.15. Yeah, this would never be a valid address. Right? Good point. Good observation. What I showed is IPv4, but it's obsolete, although used a lot today. The current addressing question. Correct. So is it a ways to give all of it? Yes, because EPFL was a precursor. EPFL asked for IP addresses in the 80s already as a research institution. And at that time, there were only universities and research centers that were using IP. So you would get whatever you asked for. So if EPFL would ask today for a block of IPv4 addresses, you would not get any. If it had asked 20 years ago, it would have got perhaps a block with a much longer prefix. So yes, it's a waste, but that's based on history. But remember, IPv4 is historical. The current version of IP is IPv6. IPv4 has 32-bit numbers. With 32 bits, you can identify how many endpoints. 2 to the power 32, which is 4 gigs, 4 10 to the 9. So 4,000 millions, which is a bit less than mankind. So we should share IP addresses. There's not one address for everyone. But as we will see, that's not a problem because, in fact, we do share addresses with things that are NATs that we will discuss a bit later. But still, there is a problem. This address space is exhausted. So if you open a new business of an internet service provider, you will not get a block of IP addresses. Instead of that, there was another, what I call numbering plan, which is called IPv6, which has multiplied by 4 the space, which means has raised to the power 4 the number of possible endpoints. And now this is believed to be a truly astronomical number. I'm not sure whether it's the number of atoms or elementary particles in the universe, which is 2 to the power 128. So this number is truly astronomical. We will never need all of it. So probably that's the final numbering plan. Perhaps in 200 years, we will be using the same. None of us will be here to check, so I can test this prediction. So that's the current numbering plan. And probably if you have a modem at home, an ADSL modem at home, you get an IPv6 address from your provider. EPFL, for some reason, who was very early and innovative in the 80s about getting this IPv4 address, became much more conservative in the recent years. And I had to work hard for 10 years until we got IPv6 openly at EPFL, and we have it this year. So you're the first generation of this course who will be able to do all the labs on IPv6 natively at EPFL. Before that, we had to have a special room where we'll give IPv6 address. Why is it so? Well, we will see that what has changed at EPFL in the meantime is that in the 80s, universities were small, everything was family style, there was not many guidelines and constraints, every lab could do whatever they wanted. Now we're run more like a bank, and there's privacy issues, and you can go to court if somebody did not delete the record of this exam and so on. So it has we have entered a different world where data privacy and security has become a real concern, and there's a lot of reluctance in moving from something that you know works into something that is new, even if it's doing exactly the same thing. It's like if you change from Windows to Mac, and essentially you're doing the same thing, but there will be a huge cost in the change. simply because lots of things that used to work in a certain way do not anymore. So you need to train you. So use waste of energy, which is one of the problems. Migrating from IPv4 to IPv6 has a number of issues that we will talk about. And the two coexist today, depending on which part of the world. Some part of the world that have been booming over the past years have only IPv6 addresses. Other parts like here, where the growth has been more moderate and has had internet before, are primarily using IPv4 addresses. The difficulty is that the two things are completely incompatible. That's a design decision. There are two families of thoughts in engineering and in computer science about compatibility. Oh, there's no clock. I should have stopped 10 minutes ago. So I'll just finish this sentence. There are two families of thoughts. There's the Apple way and the Windows way, Microsoft way. Microsoft, you talk to executives in companies and so on, and the executives, what they want is to minimize the risk, minimize disruption. So you're compatible with everything. When Microsoft does Windows 11, there are still things in it. There's still the DOS shell where you can write a command that we would write in 1986, right? So it's backwards compatibility. Apple, as you know, there is not so, when they think it's better to do that, then they stop the other thing. Like, for example, if you have an M1 processor, then your VirtualBox will not work anymore. And you have to accept that. What is good, what is bad, or we don't know. It's true that being backward compatible with everything induces a huge complexity. You continue to do things now. You continue to support a line printer with a serial interface that quasi nobody has. And that makes the software very complicated and therefore more fragile. So it's a good idea to be not compatible. But of course, it's a pain when it's not compatible because sometimes you always have something that doesn't work. So it's not clear where the best is. But the result is that IPv6 and IPv4 are not compatible. IPv6 is a new network layer. It's not IPv4 with larger addresses. When Swisscom changed their numbering plan by adding 2 digits, our telephones still continued to work, right? And I can call somebody that has a number of digits that is not the same as my telephone number. So it could be possible to be compatible, but that's not the choice here. So take-home message is they are not compatible, which means if I send an IPv4 packet to an IPv6 machine, the IPv6 machine will not understand it and vice versa. Voila, we'll do a break. We break for the 10 minutes. So we resume in 10 minutes at 23 past 1. Now we identify systems not just by addresses, but by another completely different mechanisms called names that you're probably very familiar with. So those are all names here. We'll talk a bit later in the course how the names are organized. I mean, we have .info that is used, for example, by SpeakUp, .com, .nz, .ch, which means Switzerland, etc. We'll come back to this. The thing we need to know now is that names, the reason for that was to have a human-readable alternative to IP address. So the idea that when the first web server was done, the idea is that the web server is identified by an IP address and then AT, which means web server. So www.epfl, the IP address of the web server of EPFL and port 80. But of course, this is not very human-friendly, although by now we do that for telephone numbers, right? So the idea was to do a synonym. So for example, ssc.epfl.ch, as a first approximation, we can think of it as a synonym of the IP address of the machine that runs the web server of SSC for EPFL. So that's the idea. Now it's a synonym for either IPv4 or IPv6. And the good thing is that since we have both IPv4 and IPv6, now it's very convenient to have names because then by using a name, you don't have to worry whether there is IPv4 or IPv6. Of course, when we use packets, we need to map the names to IP addresses. For example, if I go to a web server, why do I go to a web server? Well, because I click on the link, and this link says to me, for example, I want to go to this web server, followed by this name. So I have this information from another web server or an email or whatever. I know I want to go there. Now, in order to contact this web server, my machine needs to know the IP address. It needs to remove this, it needs to solve this translation. How do I know the IP address? Where? By going to my DNS server. So my machine must have a DNS server that agrees to serve me. Typically, this is done in the configuration of your machine. When your machine joins the EPFL Wi-Fi network, it acquires an IP address and also the IP address of the DNS server of EPFL, which until recently was this one. If we don't know such an address, then we're stuck, except if we know a well-known address. For example, some companies like Google agree that their web servers are served by, can be used by anyone. Most companies don't do that, because if you run a server, that costs resources, electricity, maintenance, etc. So EPFL does not agree that anybody in the world goes to the DNS server of EPFL to answer questions like, what is the IP address of something? But Google does. So you can always configure the Google address as your web server. But this is also part of the configuration of your machine in order to work with IP. So my machine is well configured. When I click on this, it will first send a packet. This one is sent over UDP because it's a single request here. And if everything works well, if this is correct here, the web server has the answer. Now here it's easy because I am at EPFL, the destination is at EPFL, and the server is at EPFL. So everything is local, all information is available in the DNS server. Of course, that works even if the remote destination would not be EPFL. We will see a bit later how this is done. This DNS server, if it doesn't know, will therefore contact another DNS server until the problem is solved here. So here, the result of this is that my web browser gets the information of the IP address of where this web service is hosted. Therefore, it will send an IP packet with IP destination, the one that I've received here. So through the transport layer interface, we will use the socket with the IP address, not with the name here. And then I put the message, which is the application layer here, which is, for example, an HTTP GET message. Then this web server, if it accepts my request, will reply with a number of things. So the binary data that may represent an image and a number of things, and a message saying that's the end. And this is sent to me. How does the web server know my IP address? We have to send it because in fact it is in the IP packet that I've sent. There is a field called source address, the goal of which is exactly to be like a reply address. If I send a postcard to you with the address of the source, then you can reply to this postcard. This is how it works. So the important thing is, of course, that the names, they are in the application layer. They are in the text that I receive. They are not in the IP packet header. When the routers in the world manage those packets to transfer them, they use only the IP addresses, not the names. That was the network layer. So we've discussed application, transport, and network layer, and we could stop there, but there is another thing called the MAC layer, which is like a small network layer, a network layer at small scale. There are different ways to present it, but the simplest way, for example, is to imagine that the MAC layer is used to interconnect system using, for example, a Wi-Fi base station or an Ethernet switch. An Ethernet switch is something where you can put Ethernet cables, you connect all your devices. If you connect all of these together, then you have what is called a subnet or a local area network. Subnet is the name we give to that when we are viewing things from the IP layer. Local area network is the name that is used otherwise here. Now, the first question you might ask is, why do we do this? I mean, why, if I need to connect 4 systems here together over Ethernet, instead of putting an Ethernet switch, I should put an IP router. the box that analyzes the header, the IP addresses. I said we send packets, and we can do that. And as I said, it's probably what we would do if we would invent things from scratch today. But this is not the case. We did not invent this from scratch. It was invented over history. And historically, this is how the first networks were done. The first networks were only at the local layer. The idea of interconnecting over a long distance things that are not in the same campus, for example, came only much later. And at the beginning, we used telephone cables for that, and not things like IP. In fact, if you think about it, the acronym IP stands for Inter-Network Protocol. Inter-network means interconnection of networks. And we think of it as the network, but it was designed as the interconnection of different networks. In fact, in the 80s, in the commercial world, there were different networks, as IBM SNA, DECnet, etc., that were not at all using TCP-IP. And TCP-IP was a mechanism to interconnect them together. But more importantly, the way to think of it is that the mental model, how this evolved over time, is that IP is a mechanism to interconnect things like I'm showing on the screen. Local things that do not use IP. So if I connect a machine over Ethernet to another one, they can communicate without using IP. And in the past, they did. Perhaps some of you, if you go to the Bolo Museum, you might see things like the AppleTalk protocol. AppleTalk is a protocol that was used to connect the first Mac to a printer. And you would connect directly the Mac to the printer without even an Ethernet switch. You would physically pull the wire here to the printer. And if you had a second Mac to connect, you could open the wires and do a connection. And it worked. It worked. That is called a local area network. And it doesn't use IP addresses. It uses instead a different mechanism that I said. Now, this is completely obsolete today. Nobody would do things in this way, so we use Ethernet switches. But the same problem exists with cellular, with radio networks. If you want to interconnect various systems together, you need to handle things like collisions. We'll talk about this a bit later. So you need to do more than just create a packet with an IP destination address. Because if A and B send together, perhaps it won't work. You need that one of them agrees when to send, and perhaps also for some systems over which code or over which frequency. So there's a zoo of complexity here. All of this is taken care of by a special type of networking that does not use at all IP addresses. So you can write some software that would allow a PC to send a PostScript file to the printer and not using TCP/IP by natively sending it using the Ethernet switch or even Wi-Fi. And that was done very much in the past with AppleTalk, for example. It is still done today in some industrial networks. But of course, this is clumsy because you don't use the standard socket interface that everybody knows and is well debugged. So this is no longer mainstream, and this tends to be obsolete. However, it keeps its presence in the form that we can think of the network layer today as being made of two parts, local area networks that are interconnected by IP. The main difference is in the addresses. The addresses used at the local area network scale are serial numbers. They are not specific of whether we're at EPFL or not. So an Ethernet adapter has what is called a MAC address. Think of it as a serial number. If you have a bicycle, probably it has a number on the frame. Or if you buy an Ethernet adapter, it has a number on it. That's its MAC address. It has to do with who built it. So whoever built it owns the block here, the first part of this block. So those are hexadecimal digits. We are smarter than with IP before. It's 48 bits in total. So 6 blocks of 2 digits. That's the way it's typically written. And they have nothing to do with each other. So if A and B are in the same subnetwork, their addresses are completely random. They might all come from this. So this is Cisco, this is Apple. So if you have two Macs, perhaps the prefixes are the same, but Apple has so many devices that it has a large number of prefixes. So those addresses appear to be random, just like that. The number that is on the frame of my bicycle, it doesn't say that I am here in Lausanne or anything like this, unlike an IP address does. So those addresses are random. They have a benefit by being random. Of course, the network is more complicated. If a packet in California has to come to EPFL, the routers in California, by analyzing 128.178, they know, oh, that has to go to Switzerland. They don't need to know in which room it is, but they know easily where to send it because it has an aggregated information. If there is a MAC address somewhere here, a router in California has no way to know where it is. So a router in California will never use a MAC address to send a packet to me because a router uses IP addresses. So MAC addresses are used only for the local scope, because by having random numbers, it's you need an exhaustive list. For example, an Ethernet switch, as we will discuss a bit later, an Ethernet switch needs the exhaustive list of all the addresses of those guys here. How does it learn it? We will see. But the main reason it is the way it is that because at the origin, those were all more like Wi-Fi, single cable, and it was completely plug and play. If I have my printer, my AppleTalk printer, connected to my Macintosh, the first time I connect them, it works. I don't need to configure an IP address in my printer. I don't need to. Now, today, you don't need to configure either, but because there are smart programs in my printer and in my Macintosh that will discover by shouting, is there a printer around? And anyone who is a printer looks for such messages and answers, yes, I am a printer. And then my software will learn there's, so this is how we do it today. But when this was done in the 80s, you didn't do that kind of programs. There was too much code. The processors were at megahertz, right? Not gigahertz. So you didn't do that kind of things. Instead, you knew immediately, if I know the MAC address of B, I can send a packet to B on the wires and it will reach B. Still like this today. If I send over an Ethernet cable, the only thing I need to reach a destination is to know the MAC address. And the MAC address doesn't need to be configured because it's written into the hardware here. So you don't need to configure your IP address, and it doesn't work if your address is false. So take-home messages, MAC addresses are hardware addresses, and they are used in the following way. When I send a packet, when A sends a packet, then all stations within the local area will try to receive it. And if they see their own address, they will receive it. Of course, this is completely unsecure. And if you do that in a Wi-Fi hotspot that doesn't use additional security, that allows sniffing very easily. In fact, this is the way how sniffers work. In fact, anybody who has the address can receive. So if B pretends to have this address, you can change by software your MAC address, then B will receive all the traffic that is meant for R, for the router. That works. This is how local area networks are built. Of course, as we will see, we add additional security mechanisms to make this impossible, to make this attack impossible. But that's the mental model of a local area network. Originally, the local area networks were what we call shared medium. Shared medium is like Wi-Fi. If I send a packet, every system in the room can potentially receive it. Only the base station, which is there, will receive it. But all of your systems could be configured as a base station and receive it. And the original Ethernet or AppleTalk systems were a physical cable that was really going from one machine to the other. When A sends a packet, it sends it and puts the destination address with the hope that only this destination address will get it. And it's the job of the hardware, the Ethernet hardware or the AppleTalk network hardware, to eliminate, to screen the bits and see whether they correspond to your own address here. Question? It is a bus, yeah. It is exactly a bus, like the bus of a machine. It is the first local area networks, that's a good remark, were essentially an extension of the machine bus that goes outside of the computer. Question?
How to be sure that the packet we send is received?
We don't. TCP will detect whether it was not received and ask for, but at this level, at least for Ethernet, we don't. Wi-Fi, as we will see as acknowledgements, there are mechanisms in Wi-Fi where if I send a packet to the base station, I expect the base station to acknowledge, at least if I don't ask for no acknowledgement, it will acknowledge it. So if the packet is lost on the way, because the radio channel is bad, I know it's not received, at least by the base station. Doesn't mean it's received eventually by the final destination, but we'll talk about all those details again. So of course, a local area network is not so exciting. That's the computers of the 80s. Right? In the 80s, computers were really not exciting. You could do a few Tetris games and things like this, but it was essentially machines for accounting, word processing, and printing. So things like this here. Of course, the interesting thing is where you interconnect all of those together. An interconnection is done by routers. So that's the mental model of computer networking today. The IP views the world as being made of subnets, local area networks that IP calls subnets, and that are interconnected. So if this computer wants to talk to that computer, if they're not on the same base station, or here on two physically different systems, we must have a router in between. Now be careful when we say we must have a router, this is computer stuff, right? So computer stuff can be incorporated, can be materialized in very different ways. Here I'm showing of 3 separate boxes, which are the switch, the Ethernet thing that interconnects the Ethernet cables, a router, and the base stations. But they could be the same box. You could have a single box that does all of this. Or you could even have software that does all of this, like what we use in the labs where we emulate everything with software. So we have to be aware that a function can be implemented in zillions of different ways. For example, TCP is typically software in your operating system, but there are also hardware systems on a chip that implement TCP in hardware for small embedded devices. So the appearance of things might deceive us. Now, because IP views the world as being a collection of local area networks, we are exposed to the first thing, which is the network mask. So that's one of the details that in principle should be discussed more later, but in order to do any lab, we're confronted with that. What is the network mask? Well, it is the size in bits of the subnet prefix. What is the subnet prefix? Well, it is the thing that for IP, the part of the prefix that identifies the local area network that we are in. At EPFL, it is 24 bits with IPv4. So at EPFL, 128.178.71 is, that represents 24 bits. If I use what is called dotted decimal notation, the notation used with IPv4, that's 24 bits, 3 times 8. And that corresponds to, that's a subnet prefix, and that's the identity in the world of IPv4 of a local area network. So you see, for example, here, there is a router, and here all the computers that are here are in this same subnet. A few years ago, that corresponded to physical wiring. For example, 10 years ago, my lab was in a given corridor, and all the IP addresses of this corridor were in the same local area network. That correspond to 138, 178, 156, for example. That was my lab, and that was my prefix. Now we're a bit more flexible, and we can allocate things dynamically. So, but that's the mental model that still permeates everything we do. And now, why do we need a subnet mask? Well, if everybody in the world would agree that an IPv4 prefix is 24 bits, then we would not need a mask. But not everybody uses the same. We want to have flexibility. For example, at ETH, they wanted to be a bit smarter, have more subnet prefixes. So their more subnets. Their subnet prefix is 26, not 24. And for IPv6, well, it's the same. IPv6, very often it's 64, half of the space, but we will see examples where it's 92 or 78, etc. So there's complete flexibility. Therefore, we need to give the number of bits. For example, we could, one notation that is very often used, in particular in the context of routing protocol, is to indicate a slash with the number of bits. So if I see this notation, it means I should take of this address only the first 24 bits, and that identifies my subnet prefix. Now, this is not done in this way. It's done using a mask. And a mask is just a very clumsy way of saying the same thing. For example, if you go to the configuration of your IPv4 machine at EPFL, you will probably find the system will tell you that the mask is this, 255, 255, 255, 0. Now, where does it come from? Where if you expand this in binary, you give this. 255 is all bits equal to 1. It's a string of 8 bits equal to 1. That's something to remember. We'll see it constantly. All bits equal to 1 in dotted decimal, that's 255 here. Now, why do we do this? Well, that's just a way of saying if I take here, if I count how many bits are equal to 1, I have 8 times 8 times 8, that's 24. So this is giving exactly the same information of that as that. Now you could ask, why do we do such a complicated thing? Well, there is a difference by giving this. In theory, I would allow the subnet prefix to be non-contiguous. So I could have a subnet prefix that is all ones here. That's EPFL part, we don't touch it. But EPFL could agree, for example, that the subnet prefix is the last 4 bits. Right? And that the host part is the thing before. In theory, you could. In practice, I've never seen it being done anywhere. So just because people thought it would be a good idea to do it, we give the subnet prefix with a mask. So that's one of the examples of things that come from history and compatibility. Hackers probably might find interesting to do things like this. If you want to hide the structure of your network, you might do things like this. Question?
So that tells you that the thing after the fault, so the bytes has only this amount of bytes for its number?
Yes. In fact, the mask, how do we use a mask as a programmer? We do typically a bitwise AND. So if I do the bitwise AND of this and my address, I will have 128, 178, 71 zeros. So we'll put zeros everywhere in the parts that are not in the subnet prefix. And this is used to do a test. This is probably the reason also it's done in this way, because one of the things we need to test very frequently as an IP machine is whether 2 addresses are in the same subnet. We'll come back to that later. But for example, if this machine sends a packet to that machine, it will not send it to the router, it will send it directly. But if it sends to this machine, the packet has to go via the router. So there is a test I need to do. Is this IP destination address in the same subnet mask, in the same subnet as me? Then if you want to program this in C and be very fast, you do the bitwise AND of my address, of the mask and my address. Same thing with the other address, and you compare. If the 2 strings are the same, we are in the same subnet. That's why it is done in this way. But of course, as a user and with object-oriented software, we probably don't care about such things. So /24 or this are the same. So putting things together, here is a local area network of some size that includes 2 LANs. Here I have a Wi-Fi network. I have an Ethernet network. They communicate together with a router. Now the router, we've seen that already. That's the system that switches the postcards, internet packets. Well, took the analogy of postcards. The intermediate systems are the routers. Intermediate system is a word that has a well-defined meaning. An intermediate, remember the concept of layer. We have layers because they communicate with each other. The application layer at my web browser speaks to the application layer at the web server. But the network layer of my machine speaks to the network layer of the router, which itself speaks to the network layer of another router, etc. So the boxes, the layer instances that are not at the end are called intermediate systems. So they do work, which is not for the source and not for the destination. So an IP layer intermediate system. That's a complicated name for a router, or for the router function, because as I said already, the materialization of a function is not sometimes the same thing. What we call a router usually has a number of functions that are not just switching packets around, but you can also log into the router. Perhaps it can do a number of things. It has a little web server, etc. So the box that we call a router, or that we call an ADSL modem, sometimes has other functions. So what I say here as router is really the function of a router, which is intermediate layer of the network layer. That means, concretely, whenever a packet arrives, in real time, analyze the destination address, find out where to send it, and send it. That's a real-time machine that analyzes destination addresses and takes decision and forwards packet. We can do the same thing at the local area network with MAC addresses. And then it's called a switch. It's called an Ethernet switch, or a layer 2 intermediate system. The main difference is in the addresses that they analyze. A layer 2 intermediate systems takes the MAC address. For example, if this printer sends a packet, this computer sends a packet to the printer, it has to put the MAC destination address of the printer, and the switch will analyze the MAC destination address. As I mentioned already, it must have an exhaustive list of all the MAC addresses of all the systems that are in its domain, in its local area network, and it will know on which port, on which cables the packet has to be sent. Of course, this switch doesn't need to know the MAC addresses of the Wi-Fi systems here, because whenever a packet will go to this system here, it will first go to the routers. So first thing to remember, router is a system that forwards packet based on IP address. A switch, also called a bridge, they are more or less synonym. A switch is a word that is misused a lot. You will see the word switching in many different contexts. The word bridging is also misused, but much less. So strictly speaking, a bridge is the name we should always use. A bridge is something that forwards packet by analyzing only MAC addresses. A router is something that forwards packets based on IP addresses. So we can put all those things together. So if I go from the web server to a PC here, we'll see that the web server code will use the socket to send a block of data. S2 is the name of the socket to which it is sending. There may be multiple sockets in a machine, just like we need several port numbers. Then this block of data will be broken into TCP segments. TCP segments are calculated such that they fit exactly in an IP packet. They're a bit smaller because the IP packet will contain additional things like the IP address. So this is what we add and obtain the IP packets. The green thing is the IP header that contains the IP address. Then we put them into my local area network. I need to add MAC addresses because that's how local area networks work. And IP networks, in principle, don't work natively. They always work via a local area network and the MAC layer. Now, the physical layer, which are cables, AppleTalk cables, or Wi-Fi or Ethernet cable, will carry the thing along my my system, and the MAC destination address should be the the bridge will forward them further by analyzing the MAC addresses, and then the MAC destination address is this of the router. That's a bit strange, but this is how it is. So when the server sends a packet, the MAC destination address is the MAC destination address that allows it to go as far as it can in the local area network. Then it reaches the router. The router gets the packet, analyzes only the green, the IP layer, gets rid of the MAC addresses here, and decides by looking at its routing table, oh, it has to go in this direction towards Wi-Fi. So it will resend those packets, but now over Wi-Fi, using a different header, which is the Wi-Fi header is a bit different than the Ethernet header, and a different MAC address. It will use the MAC address that is allowing it to go as far as possible towards the destination, which in that case is the destination, is the MAC address of Elaine's PC. And then the machine will go into Elaine's PC. The Wi-Fi hardware will receive it because the MAC address is correct. In Wi-Fi, there's also security authentication that will have to be done. So it will pass the authentication and will be accepted. Now the network layer will examine the IP header. In principle, if you receive here and you're a host, the IP destination should be you. Otherwise, it's an error because you're not a router. So if it's not you, the packet is discarded. If it's you, then the header is removed. We look at, and it's passed to the transport layer. In the transport layer, there is a port number, and the port number allows the data to be made available to a socket that hopefully is associated with this port number. If there is not such a socket, then this will break here. This will be discarded by the operating system. Otherwise, if there is such a socket, it will be stored in the socket buffer until the application program will read from the socket buffer and will receive the data here. This is how all the things fit together. Some terminology. I mentioned a TCP segment, an IP packet, and a MAC frame. Those are the three words for packets. Packets are the entities that are exchanged horizontally between two instances of layer. For example, a network layer here sends an IP packet to the network layer here. The MAC layer here sends a MAC frame to this MAC layer here. And the transport layer here sends one TCP segment to this transport layer. So you see what I said before, that from TCP, it is as if there would be a physical cable directly from here to there, because the TCP segments are sent in principle unaltered from one side to the other. We can look at it from a slightly different viewpoint, what I call the onion view. If I do, which is what you will do in this very first lab, if I look now at the packets exchange over the wire, then I will see the MAC header. That is the most external thing. The physical layer we don't see, because the only thing we see are the things that are visible to the software. So the physical layer has its own header plus physical signals, but those are removed by the hardware and delivered to the operating system. So the first thing we will see is the part of the MAC header that is not removed by the physical hardware. And the header contains a MAC packet. So the entire thing is the MAC packet called the frame. And usually in a packet, we distinguish between the header and the payload. Sometimes there is another header at the end, which is then called a trailer. So the MAC payload is the useful part seen from the MAC layer, which is here, guess what? It should be an IP packet. So the IP packet is contained in the MAC frame, and the IP packet itself contains an IP header, which contains in particular the IP destination address. And the useful thing, well, at least the useful thing is the TCP segment. TCP segment contains its own header, like the port number and the TCP payload. In fact, here and then there will be more because it will be encrypted. So it will be an encryption header and eventually the data. This is how all the things fit together, and we'll be able to see that in the lab. I will conclude with this little quiz here. Coming online in a few seconds. Well, there's a typo, but that's right. So we observe the packet here. We do sniffing. How do we do sniffing? Well, the packet is on the wire between the router and the server. We can physically break the wire and put what is called a physical layer repeater. That's one of the attacks that you can do. You break, because there is technology for extending the wires to make them work over longer distances that are called repeaters, but you can do it for attacking purpose. You break the wire, you put a repeater, and you can physically duplicate the signal and receive everything that you see. So that's what the CIA type of attack will be. Or we can do it by software on the router or on the switch here. And we look at the packets that are flowing from web server to the device here, and we look at them between the switch and the router. Which destination, what is true about the destination MAC and IP addresses? I close the poll in a second. Closing. The majority says A, which means A only, which is the correct answer. The packet should have the MAC address of the router because that's the only way a packet sent by the WAN server could reach the router. But the IP destination address is not that of the router. The router needs to look at the IP destination address to know where to send it. So if the destination address is to the router, that means the web server is sending to a web browser at the router, which is not the goal. So remember, the router are like switching systems of the post office. They need to look at the IP addresses. So there must be the final destination address here. Voilà, that's all for today.